Here we'll introduce the topic of the reduction of aldehydes and ketones. So in the past, we've talked about the oxidation of alcohols to form aldehydes and ketones. The reduction is essentially going in the reverse reaction. We have to use different reagents. We'll start with an aldehyde or ketone, and we end then with an alcohol. So we've seen where if we have a primary alcohol, if we lose two hydrogens, we can then form an aldehyde. We have specific reagents that we need to form the aldehyde. And this is oxidation. So this is what we've learned in previous units. If we start with an aldehyde and form an alcohol, we need to gain gain two hydrogens, and this is the reduction. So when we do these reduction reactions, two hydrogens will be gained by the molecule. One is gained by the oxygen to form an alcohol, the other is gained by that carbonyl carbon. So that's with the primary alcohol. If we have a secondary alcohol and oxidize that to form a ketone, let's draw out this alcohol. So we have a carbon bonded to an alcohol group. Secondary alcohol means that carbon is then bonded to two other carbon groups and one hydrogen. If this molecule loses two hydrogens, this is the oxidation reaction, and we form a ketone. If we start with a ketone and gain two electrons, I did it again. We start with a ketone and gain two hydrogens. One by the carbonyl carbon, one by the carbonyl oxygen. This is reduction. So ketones can be reduced to secondary alcohols. Aldehydes can be reduced to primary alcohols. There are two common reducing agents that we'll cover. Both of these common reducing agents must be sources of hydrogens. They also must be a source of a hydrogen with electrons to create a bond, and we call those hydrides. So a hydride source. Now remember, hydride is a negatively charged hydrogen. So a hydride has two electrons, a hydrogen with two electrons. So there are two common hydride sources that we will use for the reduction of aldehydes and ketones. One is lithium aluminum hydride, LiAlH4. And the other is sodium borohydride, sodium NaBH4. You might notice that both of these elements have an element in the third column, aluminum or boron. It has 4 electrons, and then a counter ion, lithium or sodium, which has a +1 charge. So the structures are similar, but we'll start with lithium aluminum hydride. Lithium is a spectator ion. It has a positive charge. It's in the first column of the periodic table. It's there to balance out the charge of the aluminum hydride. Aluminum hydride has the aluminum bonded to 4 hydrogen atoms. So aluminum's in the third column. When it has 4 bonds, we've seen this previously, when it has 4 bonds, it has a negative charge. Now, aluminum is stable with only 3 bonds. It is uncharged. It's a neutral atom with only 3 bonds. So lithium aluminum hydride actually reacts as if one of the hydrogens and its electrons were not bonded to the aluminum. So we have a hydride ion. This is why lithium aluminum hydride is a hydride source. And then aluminum, which can act as a Lewis acid. So really, we show one of the hydrogens leaving the aluminum. Aluminum, we've seen before, will be a Lewis acid. And hydride is a base. It is a source of electrons. It is also a good nucleophile. Now this reducing agent is extremely basic. It reacts violently with water. So to perform this reaction, a polar aprotic solvent is needed. So we use ether or tetrahydrofuran. Remember, an ether is an R group, oxygen R group. THF is a specific ether, a 5-membered ring where one of the members is an oxygen. So those are 2 common solvents for lithium aluminum hydride. If you had a protic solvent present, that would be a problem. The hydride would react with the hydrogen in a protic solvent to create hydrogen gas that bubbles out. And so then we wouldn't have the lithium aluminum hydride to complete the mechanism with. Sodium borohydride, we again have a sodium positively charged counter ion, and then boron in the third column is bonded to 4 hydrogen atoms. It has a negative charge. Similarly, sodium borohydride reacts as if one of the hydrogens has left with electrons. So this is how it is a hydride source where we have neutral boron and a hydride ion. Boron can act as a Lewis acid because it is open shell. And here we have our base / nucleophile. Sodium borohydride is less basic than lithium aluminum hydride. It can be used in protic solvents like alcohols. It can be used in non-acidic water as well. And the difference, and the reason why this sodium borohydride is less basic than lithium aluminum hydride is because of the boron versus the aluminum. Aluminum is more metallic, has more ionic character between the aluminum and hydrogen. So that bond is more like an ionic bond, where the hydrogen is the negatively charged ion. Boron is more non-metal, that is more of a covalent bond between boron and hydrogen. So it's not quite, the hydride there is not quite as strong of a base because of its interaction with the boron being more of a covalent interaction. So in the next couple of videos, we'll talk about the mechanisms of how to reduce aldehydes and ketones using these reagents.